Welcome to Applications of Derivatives, Lesson 10, Optimization, Part 1. And at this point, I've already assumed that you've read the two-page handout that I sent home, and that's why there's only 2 examples. So we're just going to get right at it because I have no idea how long this is going to take. It probably will take quite a while. So let's go right on to see Charles and trying to... Oh, that's what I wanted to say. These problems are used all the time, whether it's McDonald's trying to maximize their profit or a can maker trying to maximize volume and using the least amount of surface area possible. Yeah, there's all kinds of applications for optimization. So let's get right at Charles and his fence. Okay, so first, go ahead and read it, and then come back. All right, what is Charles? What are the unknowns? Okay, first point. What are the unknowns? That would be the length and the width of the area, right? 2. What are we trying to maximize or minimize? We are trying to maximize the total area. That's what we're trying to do. All right, 3. It says draw a picture. Hey, I got one up there for you, and I also have it on your example. Check. 4. Let's see if we can come up. Well, let's assign some variables here. We'll say that A, what do you think that's going to be? That will be area, right? Okay, we'll let X, we'll let that be the length of the large rectangle. And we'll let Y be the width of that large rectangle. And I'm sorry you can't read that. It says large rectangle. Alright, 5. Okay, let's get an equation. Ready? 5. The area is the length times the width. XY. Now that would be really cool if we could just stop right here and say, okay, there you go. Unfortunately, we've got 2 different variables. It's going to be not going to be easy to differentiate using 2 variables. So, since we can't differentiate with 2 variables, we need to come up with any secondary equations. Alright, we let X be the length and we let Y be the width. Let's go up here and look and see on our field how many lengths there are. Okay, where are we? Here we are. There's 1 length, so that's 1x. There's another length, and there's a 3rd length. So there are 3 lengths. And then how many widths to enclose the whole area? 1, 2, 3, 4. So we have 3 lengths and a total of 4 widths to make up our total of 480 yards. So now we're going to solve that equation for y, and then we'll substitute in. So for y equals 480 minus 3x. Divide both sides by y, by 4, and we have 120 minus 3/4 x. Alright, now we can use 5 and 6 to make an equation with 1 variable, maximizing the area. Area equals x times 120 minus 3/4 times x, because that's what y was. So area equals 120. Sorry about the bad writing. My stylus is not working anymore, so I can't use the slate right now. 3/4 x squared. Alright. Now we're ready to look at number 8, determine the domain. Okay. Well, if x is 0 here, if x is 0, then y is 120, and then if y is 0, then x is 160. So my domain, if you can believe it, the domain is going to be anywhere from 0, where I have absolutely no length and all width, to where I would be at the other extreme, have all length and no width. Of course, they'd be really super skinny areas and they wouldn't work real well. So 8, the domain, somewhere in between there. That's just so we don't go outside the bounds. Number 9. I think we're now ready to find out. Let's go ahead and take a derivative of the equation in number 7. So that would be a prime equals 120 minus 3/2 x. Okay, we'll set that derivative equal to 0. 120 minus 3/2 x, and not so easy to write with the mouse. 3/2 x equals 120. Multiply both sides by 2/3, and x will equal 80 yards. Now we have to make sure that that is a maximum. We always got to check to make sure that that is a maximum. Right here at 80, the endpoints are 0 and 160. Alright, what was A prime again? Right there it is. So let's pick 10. 120 minus 15, that's positive. And let's go ahead and pick 90 here. No, 100. Really, yes, we'll pick 100. Okay, 120 minus 150. 3/2 of 100 is 150 negative. Yes, that is a relative maximum. So we have maximized the area by making the length 80 yards. So the length is 80 yards. Oh, I really got to fix this before I can do the next example. I'll tell you that right now. And the width, go ahead and put that back into the equation that you found for 6. And when you do that, you will find that the width is 60 yards. So that will maximize the area. All right, let's move on to the next example. All right, so here we go. The unknown. What is the unknown in that? Yes, the unknown is definitely how much to charge, the toll. 2. Sorry, the cursor's off. I'm just going to go in. What are we trying to maximize on this one? We are trying to maximize total revenue. Yes, that is correct. That's what we're trying to maximize. 3. That was a guess. I don't even know where my cursor is. I kind of lined it up. Draw a picture. Can't really draw a picture on this. Number 4. We're going to make R equal the total revenue. We are going to make T equal the toll in halfpennies. We're going to make N equal the number of vehicles using it. And we're going to make A equal the additional vehicles that will use it as we bring the price down. Whew. That is quite a smattering of things. Alright, let me extend the page a little bit. Let's see if we can come up with an equation. Think we can come up with an equation? 5. Wow, I totally missed that, but that's the way it is. The revenue equals the toll, however much we charge, times N, the number of vehicles. Okay, and this is by far the hardest part right now, is coming up with some additional equations and changing this into an equation of all one variable. That's definitely the difficult part. Any additional things we can do? We need to get A in terms of the additional vehicles in terms of T and N. So let's see here. We have N equals the number of vehicles equals 6,500 plus any additional vehicles that we can get. We can also come up with the additional vehicles will be 100 extra for every penny that we make it less than 175. So N, I'm going to substitute A in up at the top here. I'm going to put this A right here into there. N equals 6,500 plus 17,500 minus 100T. So N equals 24,000 minus 100T, the number of vehicles. Hey, guess what? I can now make a new equation, number 7, using just, move down a little bit, 7 R equals T times 24,000 minus 100 T. R equals 24,000 T minus 100 T squared. Okay, there is the function now in terms of one variable. And yes, that is by far the hardest thing to do with optimization, is to come up with an equation in one variable. So go ahead and take the derivative of that and come back. Okay, R prime is 24,000 minus 200T. Set that derivative equal to 0. 24,000 minus 200T. 200T equals 24,000. So the total, the price in halfpennies, should be 120 halfpennies. Alright, what I want you to do is I want you to use the first derivative test to make sure that that is a relative maximum. And then you'll find out that it is, and that will maximize profit. And it'll be 100,440,000 halfpennies. This concludes Applications Derivatives Lesson 10.